refraction of light is another beautiful phenomenon of light. We will see what happens in case of refraction of light in the next few slides. So let us now look at what is refraction of light. Till now we spoke about the reflection of light, which meant the bending or the bouncing back of light when it strikes a boundary between two media. So what is refraction now? It is the bending of light when it passes from one medium to another. So that means there is no bouncing back now. It says that light will pass from one medium to another, but the ray of light, instead of going straight, it will bend a little. So that is known as refraction of light. There are several examples around us where we see this phenomenon of refraction. For example, the first picture depicts a pencil dipped in a glass of water. You can try it on your own. Take a glass of water, put a pencil inside that water. What do you see? That the pencil appears little bent, as you can see here also. Right? Why does this happen? The pencil is not at all bent, right? It is a straight pencil. But due to the refraction of light, because here light rays are entering from one medium to another. One medium is air, the other medium is water. So when it enters from one medium to another, light rays bend. Now due to this bending of the light rays, the object appears little different than what it is actually. Similarly, if you look at this aquarium, you see that there is a fish which is visible in a different way. I mean, you see the actual position and the apparent position. I mean, the position where the fish actually is and the position where you are viewing the fish are different. That is again due to the phenomenon of refraction, because here also two medium are involved, air and water. Similarly, the rainbow which you see in the sky is also a result of refraction of light. Mostly you would have seen that a rainbow is observed after a rain. I mean, after rainfall, when one part of the sky is little sunny, whereas the other part is little cloudy, you generally see a rainbow. So this rainbow is also formed as a result of refraction. So we will discuss about the formation of rainbow in detail in one of the later slides. So for now, let us try to focus on the phenomenon of refraction. What actually happens in refraction? Now, similar to reflection, there are two laws of refraction as well, which has to be universally followed wherever refraction takes place. Now, in case of refraction, again we have some of the terminologies. That is the incident ray, the ray which falls on the surface between the two media. In this case, let us suppose this is medium 1, this is medium 2. This is my incident ray and this is my refracted ray. Right? Because here if you see, the incident ray should have gone like this, but instead of that it gets slightly bent. So this becomes your refracted ray, and this normal is again the same thing, that is perpendicular to the surface. So the first law says that incident ray, refracted ray and normal to the interface at the point of incidence all lie on the same plane. So it is similar to the law of reflection, which says that the incident ray, reflected ray and normal should lie on the same plane. So this also says the same thing. The second law says that the ratio of sine of angle of incidence to sine of angle of refraction is a constant for a specific light of a specific color and for a specific pair of media. That means in this case, this is my angle of incidence, that is the angle which is formed between the incident ray and normal. Similarly, the angle formed between the normal and the refracted ray is known as angle of refraction. So here theta 1 is angle of incidence and theta 2 is angle of refraction. So the second law says that sine of angle of incidence by sine of angle of refraction is equal to constant. Now this ratio will remain constant only for a specific pair of media. For example, if this is air and this is water, so the value of sine theta 1 by sine theta 2 will remain same only for this pair. Now if you keep glass instead of water, the value of this ratio will change. So that means this is constant only for a specific light of a specific color. That means for a light of a specific wavelength, because if the color of the light changes, the wavelength also changes. So this is true only for a specific pair of media and for a specific wavelength of light. So this law is often known as the Snell's law. This is often known as the Snell's law. It is named after the scientist Snell. Okay. So now we will introduce a new term that is known as the refractive index. Now, what is refractive index of a medium? So what is this refractive index? Now, as I told that whenever light enters from one medium to another, the ray of light will bend. Now, there has to be some parameter to measure that how much bending of light will take place. There has to be some factors which will determine that okay, light will bend this much when it moves from this medium to this medium, it will move that much when it moves from this medium to this medium. So there has to be a measure of bending of light. So that is why this refractive index was introduced. It is the measure of bending of light during refraction. That means how much or to what extent is the ray of light bending when it enters from one medium to another medium. So how is it defined? It is defined as the ratio of the sine of angle of incidence to the sine of angle of refraction. Just now we saw in Snell's law that sine of angle of incidence to the sine of angle of refraction is constant. Now this constant is nothing but, this constant is defined as the refractive index. So we define this constant as N21. It is often denoted like this. That means this is refractive index of medium 2 with respect to medium 1. Let us suppose this is medium 1 and this is medium 2. This is the normal to the medium. This is the ray of light. This is I and this is R. So we say that sin I by sin R is equal to N21, that is refractive index of medium 2 with respect to medium 1. So this is how we define refractive index of a medium. It is also defined as the ratio of velocity of light of a given wavelength in empty space to the velocity in a medium. So that means we are comparing the velocity of light in a medium with respect to vacuum. So we also define refractive index of 2 with respect to 1 as c by v, where c is the velocity of light in vacuum and v is the velocity in some medium. Now there is another important relationship, that is refractive index of medium 2 with respect to 1 is equal to 1 divided by refractive index of 1 with respect to 2. So they are reciprocal of each other. Right? Refractive index of 2 with respect to 1 is equal to 1 upon refractive index of 1 with respect to 2. Now, from these definitions of refractive index, we can say that refractive index depends on nature of the medium. That is absolutely correct, because this velocity will depend upon the medium. If it is water, the velocity of light will be different. If it is glass, the velocity of light will again be different. So that means the value of refractive index depends or changes with the change in medium. It is independent of angle of incidence. Right, so nature of the medium is the only thing that governs the value of refractive index. It doesn't matter at what angle of incidence the incident ray falls on the surface between the two media, right? So the only parameter, that means refractive index is a unique for every medium. Every medium has a refractive index of its own. Now depending on the value of the refractive index, we can then judge the bending of light, how much the light will bend. Refractive index is the parameter which will tell us about the optical density of a medium. For example, whenever we talk of medium, we categorize them into two types. We say optically rarer medium and optically denser medium. So in this case, when we talk of density, we are not talking about mass density. We are talking about how dense is that medium to refract light. If the medium has very high refractive index, that means we say that it is optically denser medium. That means if light enters into that medium, the bending will be more. Similarly, if the value of the refractive index is very less, we say that the medium is a optically rarer medium, right? So value of refractive index also tells us about the nature of the medium. And the properties of a specific medium determines how much refraction will take place in that medium, or how much bending will take place in that medium. So whenever we talk about optically denser medium, it has higher refractive index. Optically rarer medium always have lower refractive index. Let us take this example. Let us suppose I have two medium 1 and medium 2. Now let us suppose if I say that n21, what is n21? Refractive index of medium 2 with respect to medium 1. If n21 is greater than 1, what does this mean? This means that refractive index of 2 with respect to 1 is greater than 1. This means that refractive index of 2 by refractive index of 1 is greater than 1, or it means refractive index of 2 is greater than refractive index of 1. This means that medium 2 is a denser medium and medium 1 is a rarer medium. So here denser and rarer means optically denser and optically rarer. Similarly, if we say that n21 is less than 1, this implies that refractive index of 2 is lesser than refractive index of 1. This means that 2 is a rarer medium and 1 is a denser medium. Now please make a note that here optical density is not related to mass density of the medium in any ways. Mass density talks about mass per unit volume. But when I talk about optical density, it means how dense or how much more dense or how much less dense is the medium to bend a ray of light. So if the refractive index is more, it will bend the light more. If the refractive index is less, it will bend the light less. Right? So now you understand the significance of refractive index and why it is called refractive index. It is called refractive index because it is an index which defines the extent of refraction. That is how much refraction will take place. So now in the entire lesson, instead of using the term optically denser and optically rarer, we will use the terms rarer and denser medium. Right? So now let us see what happens when a ray of light enters from a rarer medium to a denser medium. Now whenever a ray of light enters from a rarer medium to a denser medium, it always bends towards the normal. Now why does that happen? Let us look at it. Let us suppose this is medium 1 and this is medium 2. This is my rarer medium and this is my denser medium. This is the normal, and let us suppose this is my incident ray. So now it will bend, that we know, but how much will it bend and how will it bend? Now from Snell's law, what do we know? We know that sin I by sin R is equal to n21. That is refractive index of 2 with respect to 1. So now we are telling that 1 is rarer medium and 2 is denser medium. That means from the previous slide, we can say that this implies n21 is greater than 1. That means refractive index of 2 is greater than the refractive index of 1. Now if n21 is greater than 1, then we can say that sin I by sin R, which is equal to n21, is also greater than 1. That means sin I is greater than sin R. So from this we can say that I is greater than R. So this angle of incidence will be greater than the angle of refraction. That means this angle should be smaller. So when will this angle be smaller? Let us suppose if there is no bending, then it should go like this. In that case, angle I and angle R will be same. But whenever bending is there, if it moves towards the normal, then angle of refraction will be less. Right? So that means in this case, the refracted ray will bend towards the normal. right? That is why a ray of light moving from a rarer medium to a denser medium always bends towards the normal, whereas a ray of light moving from a denser medium to a rarer medium moves away from the normal. We can prove this in a similar manner. Let us suppose here we have medium 1 and medium 2. This is denser and this is rarer. This is my normal. This is my incident ray. This is the angle of incidence. Now in this case what will happen? Sin I by sin R here also is equal to n/1. Now in this case, since 2 is rarer medium, that means n/1 will be less than 1. That is n2. This implies sin I by sin R is less than 1. This implies I is less than 1. That means angle of incidence is less than angle of refraction. So that is possible only when this ray goes away from the normal. In that case, angle R will be greater than angle I. Right? So here in this case, the refracted ray goes away from the normal after refraction. So that means now you are getting the idea that when a ray of light enters from one medium to another medium, due to the difference in refractive index, it either bends towards the normal or it bends away from the normal. And this bending of light is known as a refraction of light. Now let us look at the phenomenon of refraction through a glass slab. What happens when a ray of light passes through a glass slab? That is, it first enters from air to glass slab, then again it moves from glass to air. That means there are two transitions. First there is a change in medium when it enters from air to glass. Again there is a change in medium when it moves from glass to air. Now what happens in this case? Let me name this medium as medium 1, this is medium 2, and then again this is medium 3. These are the three different mediums through which the ray of light passes. What happens when this incident ray strikes this medium between 1 and 2? What is the normal to the medium? This is my normal to the surface, right? So this is my angle of incidence I1 and this is the refraction because it enters from a rarer medium to a denser medium. Because which is a denser medium? Because the refractive index of air is 1 and the refractive index of glass is greater than 1. So glass is a denser medium than air, right? So it is entering from a rarer medium to a denser medium. So it bends towards the normal and then again it moves straight. Again it reaches at this point when it enters from a denser medium to a rarer medium. So what it does, it goes away from the normal. So in this case the angle of incidence is I2 and the angle of refraction is R2. So what do you see? This was your incident ray which entered the glass slab and this was the ray which emerged out from the glass slab. So this ray is known as the incident ray because it was incident on the glass slab. This ray is known as the refracted ray and this ray which comes out of the glass slab is known as the emergent ray. Now what do you see? You observe one interesting thing, that if you assume that there had been no glass slab, had there been no glass slab, your incident ray would have moved straight like this. Now, if you see, if there would have been no glass slab and if somebody would have observed, he would have observed this incident ray, right? But now if you place a glass slab, the ray which is coming out is this emergent ray and this emergent ray will be visible to somebody who is observing it. So that means somebody who is observing an object is not observing the real position of that object, because there is a lateral shift involved between the actual incident ray and the emergent ray, and the emergent ray is the one which reaches the eye of the observer, and as a result, let us suppose if this ray reaches the observer's eye, he will assume that the object or the incident ray is coming from some point here. So that means, but actually the incident ray's source is here. So the person will observe this point. So the person will think that the source of the incident ray is here, and this is the result why because of this change in medium or because of the phenomenon of refraction, we often do not observe the actual position of the object. Now, in one of our previous slides, I gave you some examples of refraction, right? Those examples you can understand or you can explain those examples on basis of this concept, right? So now, in this case, another important thing which we can discuss is refractive index of medium 2 with respect to medium 1 will be equal to 1 by refractive index of medium 1 with respect to medium 2. Similarly, refractive index of medium 3 with respect to medium 2 will be equal to 1 by refractive index of medium 2 with respect to medium 3. What would be the refractive index of medium 3 with respect to medium 1? Let us suppose in this case we have medium 1 and medium 3 as same. Let us suppose if we have some system where we have medium 1, medium 2 and medium 3 and they are all different medium. Let us suppose this is air, this is glass and this is water. So in this case, this relation will hold true. Now what would be refractive index of 3 with respect to refractive index of 1? It would be 1 by refractive index of 1 with respect to 3. Now in such scenarios, I can also say that refractive index of 3 with respect to 1 is equal to refractive index of 3 with respect to 2 multiplied by refractive index of 2 with respect to 1. So this is another important relationship which relates the refractive indexes of 3 different media. Right? So I hope you understood the phenomenon of lateral shift. This phenomenon of lateral shift is extremely important in the phenomenon of refraction. So what is lateral shift? Lateral shift is the phenomenon in which the emergent ray shifts laterally from the actual incident ray, right? This is the phenomenon of lateral shift due to the phenomenon of refraction, right? So now let us discuss the same examples once again, that why did all these things happen. Now let us look at the first example. Why did the pencil dipped in water appear bent to you? That's because when you are observing the pencil, you are observing on the lines of emergent ray. So the source of the incident ray is something different, but you are observing something different that is along the lines of the incident ray, and that is why you are not observing the actual position. Instead, you are observing the apparent position of the pencil. Similarly, in this case also, why is that? You are observing a different position of the fish. That's because the light ray coming out from this fish, it suffers a refraction as it comes out from this denser medium to rarer medium. That is, it is coming out from glass to air. As a result, it suffers refraction. So when it reaches our eye, we observe the emergent ray and we try to see the object along the lines of the emergent ray. So we do not see the actual position. Instead, we see an apparent position of the object. Now, if you consider the example of rainbow. In a rainbow also same thing happens. However, understanding rainbow is little, it's not that complex, but at least there are a few more details that need to be explained. So we will take up the example of rainbow in our next lesson when we talk about the natural phenomenon or the atmospheric refraction. Because for this we have a separate topic called atmospheric refraction, where we will see how refraction takes place in atmosphere. So rainbow is one such example. We understood what is refraction of light, right? So now we will see how does refraction takes place by lenses, right? Like how we studied the reflection of light by mirrors. Similarly, we will talk about refraction of light by lens. So here we will first see what is a lens. So what is a lens? It is a transparent optical medium bounded by two surfaces, at least one being spherical. So that means it is an optical medium, transparent, which has two surfaces. Now one of the surfaces has to be a spherical surface. That means there are different types of lenses that can be formed. You can have one spherical surface, one plane surface. You can have both spherical surfaces. You can have both spherical surfaces in this way. you can have one spherical surface and another as well spherical surface. So there are different types of lenses that can be formed by different combination of spherical surfaces. However, we divide lens into two broad categories, that is simple lenses and compound lenses. Now what are simple lenses? Under simple lenses you have all these different lenses which are formed by combination of one spherical surface and another spherical or plane surface. For example, this is formed by two convex surfaces, that is called a biconvex lens. This is formed by one plane and one convex, therefore called plano-convex. This is made up of one concave and one convex, so it is called positive meniscus or concavo-convex. Similarly, this is made up of two convex, so this is known as negative meniscus. This is made of one plane and one concave called plano-concave. That is made up of two concave and therefore called biconcave. So by combination of different spherical surfaces and plane surfaces, we get these different types of simple lenses. And what are compound lenses? They are nothing but combination of simple lenses. That means two or more simple lenses when combined together form a compound lens. You generally see these compound lenses in the lenses used in cameras or video recorders. So in things like that you have compound lenses. That is an arrangement of combination of simple lenses. Now in this lesson we will focus on biconvex and biconcave lenses. So we will not talk about other types of lenses. We will only talk about biconvex and biconcave lenses. You'll learn about those other kinds of lenses, and you'll learn about these lenses in more detail in your class 12th. So let us try to understand the terminologies related to lenses, like how we did for spherical mirrors. So since now you have got an idea of the spherical mirror, it will be easier for you to understand the concept in case of lens. So first we will talk about the optical center in a lens. What is the optical center? Optical center is the center of this lens. Now here we have taken the example of a convex lens. Now biconvex lens is often referred to as a convex lens. That means both the surfaces are convex. Similarly, biconcave lens is often known as concave lens. So throughout the lesson we will be talking about convex lens and concave lens. So when I talk about optical center, it is denoted by a capital O, and it is the center of this lens. So this point is known as optical center. So it is similar to what we called as pole in case of a spherical mirror. So this is analogous to pole. Next is the principal axis. Here also principal axis is the same line which joins this optical center with the radius of curvature. Now here what would be the radius of curvature? This spherical lens is a part of a sphere. Similarly, this spherical lens is a part of a sphere. So both the spheres will have two radii of curvature. Now those points will be joined to the optical center through a line, and that line is known as the principal axis. So here this is my principal axis. Next is the center of curvature. So again the same thing. It is a part of a sphere, and the center of that sphere is known as the center of curvature. So this spherical surface will have one center of curvature. Again, this spherical surface will have another center of curvature. So there will be two center of curvature involved here. Radius of curvature, again here we will have two radii of curvature. One radius will be the radius of this sphere. Another radius will be the radius of this sphere. Right? So here radius of curvature is denoted by R1 and R2. Similarly, center of curvature is denoted by C1 and C2, because we have two centers of curvature, two radii of curvature. That is why we have denotions for two. Next is principal focus. So what is principal focus in case of a convex lens? Now here in convex lens we see that when rays of light parallel to the principal axis falls on this lens, after passing through the lens they bend as expected, right? That is because it suffers refraction. It enters from a rarer to denser, again from denser to rarer. So as a result of refraction, it is seen that the rays of light appear to converge at a point. Now this point, as per definition of principal focus, what was the definition of principal focus? It was the point where the rays of light parallel to principal axis after reflection should converge or appear to converge. So in this case, we see that in case of a convex lens, the rays actually converge at a point, and this point is known as the principal focus of this lens. Now in case of concave lens, what do we see? This is a concave lens. We see that the rays of light after passing through the concave lens, they diverge out. They do not appear to converge at a point. However, they are extrapolated at the back and they are virtually made to converge at a point. So this point is known as the principal focus for a concave lens. Right? So in this case, one interesting thing which we note here is, here convex lens is the converging lens, right? Because here the rays of light actually converge after refraction, whereas a concave lens is a diverging lens because the rays of light appear to diverge after refraction. So this is just the opposite as was in case of mirror. In case of mirror, a concave mirror was a converging mirror, but in lens, a convex lens is a converging lens. So please remember this, do not get confused. A concave mirror is always a converging mirror and a convex lens is always a converging lens. See, as I'll give you a personal suggestion here, that when you go through this lesson, first understand the mirror part very clearly. So once you understand the mirror part very clearly, only then start studying lenses. Otherwise you might get confused, because if you study the entire lesson, just at one go, sometimes what happens is people get confused that which mirror is converging, which lens is diverging, so they get very much confused. So it is better that first you become thorough with your spherical mirrors, only then you start studying lenses. That will make things better, right? So what do we see here? So here we spoke about optical center, centers of curvature, radii of curvature, principal axis and principal focus. So now we will study the image formation by spherical lenses. Similar to spherical mirrors, there are certain rules that has to be followed for image formation by spherical lens as well. So let us quickly look at the rules. So here comes the first rule. It says that a ray of light incident on the lens parallel to the principal axis after refraction passes through the second principal focus. Now from where did we get the second principal focus? This is again another interesting thing. So let us again go back to the previous slide. So here if you see, since you have two spherical surfaces, it is like a combination of two spherical surfaces. So that is why you have two centers of curvature. That is why you have two radii of curvature. Now, if you have two radii of curvature, that means you will have two principal focus as well. Because this is, when you consider this convex lens, there are two convex surfaces. For this convex surface, you will have one focus. Again, for this convex surface, you will have another principal focus. So you will have two principal focus as well. That is why we call it as principal foci. So the focus of this surface, the focus which is on the left hand side, that is known as F1, right? And the focus which you see on the right hand side is known as F2. So this is my F2, that is also known as second principal focus. And the focus of this surface, which lies somewhere on this side, is known as F1. That is the first principal focus. So there are two principal focus, first principal focus and second principal focus. Right? Now we will, at your level, as per your syllabus, we will not talk much about the two different radii of curvature R1 and R2 or F1 and F2. We will only look at a broader picture. We will just see the behavior of the lens when incident rays fall on it. You will know in more detail about first principal focus and second principal focus in your class 12. In case you are interested to know about it now, you can refer the videos of ray optics of class 12. Okay, so for now we will keep it here and we will see what happens in the first rule. So first rule says that, so just to remember, you remember it in this way, that first principal focus is the one which is on the left hand side of the lens, whether it is a concave lens or a convex lens, and second principal focus is the one which is on the right hand side of the lens, right? So a ray of light which is incident on the lens parallel to the principal axis, after refraction it passes through the second principal focus. So this is how it passes through in case of a convex lens. In case of a concave lens, it diverges. So if you try to extrapolate it, it appear to pass through the second principal focus. Now in this case, it is not passing through the second principal focus, instead it passes through the first principal focus. So this holds true only in case of a convex lens. In case of a concave lens, it appears to pass through f1. So in this case, appear to pass through f1, right? Now let us look at the next rule. Rule number 2. It says a ray of light passing through first principal focus after refraction should move parallel to the principal axis. So if you see, these laws are exactly similar to the laws which we studied in case of spherical mirrors. Here the incident ray passes through the first principal focus, so after refraction it goes parallel to the principal axis. Similarly here, the ray of light falls on this mirror, it passes through this principal focus f2. I mean, if you see here in convex and concave lens, your first and second principal focus gets reversed. In this case, if it passes through first principal focus, in this case it will appear to pass through the second principal focus, right? So after refraction it goes parallel to the principal axis, right? So here it appeared to pass through f2. And the third rule, which says that a ray of light passing through the optical center should go undeviated after refraction. So that means if a ray of light passes through the optical center, there should be no bending of light at all. So these are the three rules which basically governs the image formation in case of lenses. That means in lenses we have just three rules. One is it passes through optical center, goes undeviated, it goes parallel to principal axis, then after refraction it passes through focus. If it passes through focus, after refraction it goes parallel to the principal axis, right? So if you remember the picture of the lens, if you remember how the lens looks like and where is my first principal focus, where is my second principal focus, then you can easily plot the ray diagrams and there is no need to memorize the rules. If you understand them, there is no need to memorize. Now keeping these rules in mind, we will again go ahead and we will try to see the image formation by convex lenses and concave lenses separately for different object distances, like how we did for